the next two lectures for this week, Eli and I are going to be talking about forecasting and how we can actually tell that our models are good or performing well. And so today I'm going to be largely talking about some properties that many of you are probably familiar with already, model selection, but then getting into cross-validation and performance, and especially thinking about the modifications that we need to use for cross-validation when we're working with time series data to get or select the kinds of models that we want to have good predictive accuracy. Okay, so just basically the three things we're going to highlight are some background approaches for model selection. This is probably the review for everybody. Then we'll get into some cross-validation and thinking about some applications. And then finally talking about quantifying forecast performance and different ways we can do that, both in a maximum likelihood and Bayesian framework. The overall lecture, I think the overall material today is it's going to be shorter than normal. So I think that, it'll be done within an hour or so. Okay, all right. So how good are our models? I think there's any number of ways that we could think about to kind of characterize this. We might want to build a set of models that do a really good job explaining our data, and that would select one whole class of models. Or we might want to just focus on kind of the predictive ability of these models to predict future data. And so in that prediction could only be forward-looking, and so we're doing forecasting. It could be doing looking back in time, so doing hindcasting, or we could be doing some balancing of these two attributes. So the ability to both explain the data that we have in hand, but also make predictions in the future for data that are kind of out of sample or data that we haven't yet collected. And so, just using one of the data sets from Mars, we can just illustrate, simple linear regression. Everybody's already, knows this. This is super easy. We're just going to do, a regression in log space on one of the counts of sealed data sets from the Mars package. And then when we do models like LM, it's super easy to look at the model output and see summaries. Like at the bottom, we get your R squared. Or sum of squares. Those things are super easy and cheap to calculate, and that's really appealing because it's right there as part of the model output. But when we use quantities like sum of squares to select among models or identify which variables are most important, that's potentially problematic because as we start adding more and more variables to our models, we get better and better fits, and inevitably that reduces the sum of squares. And there's no trade-off there. There's no cost of overfitting. And so the more more parameters you add, that's just going to keep getting better and better. So we need to have some penalty for adding too many variables when we're doing those kinds of model selection exercises. And that's where these kinds of ideas, or people refer to this as kind of Occam's razor, or the principle of parsimony. The principle of parsimony being, choosing the simplest possible model that does a pretty good job at explaining the data that we have in hand. And so the parsimonious model will attempt to do both of the things that we might be interested in, both explaining the data that we have in hand and making predictions for future unseen data. And so that model is also going to be the one that kind of minimizes the bias and the variance when we're thinking about the different axes. This curve is something that I think everybody's seen, especially if you're familiar with some of the kind of classical work in this in ecology. We have the x-axis being model complexity, so this is adding more parameters as we go left to right. The y-axis is essentially our prediction error, and as we add more parameters to the model, we can kind of trace the blue line and see that our model is getting better and better, closer to truth. So it's going to be less unbiased as we are overfitting the model more. But the trade-off there is with the variance. And so as you start adding more and more predictors, you're going to be having more parameters to compute, and that's going to generate uncertainty. And when we're starting to make predictions, those overfit models will have very high variance. And so ideally what we want to think about is something like the yellow line at the top, which is kind of minimizing the bias and the variance, and we want to find that sweet spot between those two. These are just two sample curves, the red and or three sample curves rather. And for any particular data set or set of models, you could potentially build these curves, but they're going to look different probably for any real world application. Okay, so the most famous quantity that everybody's familiar with is AIC, or Akaikis information criterion. And so this is a tool that is done in maximum likelihood. It attempts to balance kind of the goodness of fit of a model against the number of parameters that we're including. And it's based on this deviance quantity. Deviance shows up all the time in these model selection tools or metrics. And so the deviance is just double the negative log likelihood, which is a quantity. If we're doing maximum likelihood, we want to calculate the maximum likelihood. So we have to generate this anyway. So the deviance is just part of that exercise. Because of the minus sign in front of the deviance, lower values are better. And just remember, maximizing the likelihood is the same thing as minimizing the deviance because of that negative sign. Okay, so why the focus on AIC? AIC and its variants have been really heavily used in ecology and related fields. And so there's a link to the Burnham and Anderson book here that most people are probably familiar with. But also when you start digging through kind of the tools that people are using in R or in Python to do model selection among huge sets of candidate variables, you'll see that AIC is one of the most commonly used tools for that people have implemented for doing this kind of stepwise model selection procedure where you add and delete variables, or this exhaustive parameter search where you combine all of the potential combinations of covariates that you might have to find the model with the lowest AIC. So this is just a handful of the kind of the popular packages out there, but all of them are using AIC as an option to do that model selection. So it's AIC, like I said, it's in all these packages. It's very accessible. It's also in the MARSS package, and I think that we've already used that. So when we use this, I'm calling these approaches like AIC, these information theoretic approaches are generally referred to as these IC approaches because there's lots of different variants of AIC. And so for where they differ is really, they all have this deviance term, which is kind of the first quantity here on the left is just that deviance. Where they differ is really the quantity on the right. So the penalty for adding too many parameters is what this part represents. And with AIC, the penalty is always referred to as 2 times the number of parameters, or 2 times k, and this is constant. So that's kind of what we're starting with. One thing you'll note is that as you start to collect more data and you increase your sample size, n doesn't appear anywhere in this penalty, and so the penalty is fixed regardless of your sample size. It just is determined by whether you have an intercept in the slope in a model, or an intercept, a slope, and an interaction term, for example. So there's no penalty here or anything related to sample size. I think that a number of you are also familiar with the small sample version of AIC, and so this is kind of a correction for particularly small data sets. And so the penalty here that used to be 2k in the small sample version of AIC is just replaced with this term here, where k again is the number of parameters, n is the sample size, and we can ask kind of what happens to this term on the right here as our sample size, our n, increases. And so as n gets infinitely large, this whole term is going to go to 0, because this will all be this will be a very large number on the bottom, and this will still be 2 times k plus 1 on the top. So this converges to AIC as our sample size gets large. I think the rule of thumb in the Burnham and Anderson book is roughly when you have a sample size less than 30, using the small sample version of AIC is a good tool, but it's really there's kind of some wiggle room there. So again, like AIC, the small sample variant of AIC is in a lot of the stepwise packages that people use for doing that kind of data dredging, or kind of weeding through lots of models to figure out which has the best predictive performance. All right, so as I said before, AIC is really trying to find the sweet spot of those two curves that I showed, where we're trying to minimize the bias and the variance for our model as we add parameters. There are potential downsides of AIC, and so AIC has a tendency to over penalize, especially when we're doing a lot of complex models with interactions, for example. So people have started to think about alternatives to AIC for a long time. These are not new. One of the other variants of this is also BIC, or the Schwartz information criterion. And so even though it's called the Bayesian information criterion, it's not at all Bayesian. It's also maximum likelihood based, but it relies on a Laplace approximation to the posterior distribution, which just basically is meaning that it assumes that if you have a model with several parameters, it assumes the posterior distribution of those parameters is going to be multivariate normal. And so, if that's a reasonable approximation, then BIC might work for the kinds of models that you're working with. So again, same format. BIC just has this deviance term on the left, and here we're also including the sample size, but we're including the sample size, or the log of the sample size times the number of parameters is going to be our penalty. And so this can be compared and contrasted to AIC, and a lot of people have done that. Just like AIC will over-penalize, BIC unfortunately under-penalizes, so there's no perfect tool here. When we kind of compare and contrast the differences, I think one of the important, there's a lot of ecology papers that talk about this sort of thing, but there's just some philosophical differences about kind of AIC and BIC and when to use each. I think one of the biggest ones is that when you're using BIC, you assume that one of your models, if you're assuming that you're comparing the fits of say 10 different models and looking at BIC to tell you which one is best, BIC is going to assume that one of those models is truth, and so it's the one that generated your data. And so what that means is that as you remember the sample size appeared in our penalty for BIC, and so the penalty was k times the natural log of n, and as n goes to infinity, what happens is BIC assigns more and more weight to the model that fits best. So if you have 10 models in your candidate set, it's going to pick which of those 10 is the absolute best model, and it's going to assign all the weight eventually to that single model. Versus with AIC, that doesn't really happen, where again, AIC isn't a function, the penalty isn't a function of the sample size, and so because AIC doesn't assume that one of those models is the true model that generated your data, that with that weight doesn't end up going to 1. So that's a subtle difference, but it's something to think about as you're kind of thinking about which of these to use. I think in terms of the time series aspect of it, these tools are also very popular in doing time series predictions or figuring out kind of the correct moving average or autoregressive order for a time series model. And so there's been a lot of thinking about how AIC or BIC relates to other things that we might be doing, like leave one out cross validation. And so AIC has this nice property of if you were to do leave one out cross validation, kind of the extreme version of that is you leave out every single point in your data set, use the others to predict it, and then keep repeating that as you kind of work your way through every point in your data set. And so when you do that, AIC is actually an approximation to that leave one out cross validation. And so they should give you the exact same answer, which is great. And BIC does something that approximates, instead of doing the leave one out cross validation, BIC approximates k-fold cross validation, where instead of holding out each data point in turn and making a prediction based on the others, BIC will, if you're doing say 5-fold cross validation, that means you split your data into 5 parts, use 4 of the parts to predict the 5th, and then kind of work through the other 4 parts in the same way. And so I think that's an important difference. The predictive ability and relation to leave one out cross validation is why AIC has seen a lot of use in the time series world, though. So for making one step ahead predictions, AIC should give you the same thing as leave one out cross validation. All right, so as I was talking about last week, so that's kind of the intro to where where we are with the maximum likelihood model selection, and thinking about selecting a model that explains our data well. But there's also this whole other world of Bayesian methods. And so the big difference, as I said last week, is kind of the maximum likelihood methods are taking your likelihood and finding the set of parameters that's going to find the absolute best peak on that likelihood surface, versus the Bayesian methods are going to be taking the whole surface of your parameters into account and asking via integration what set of parameters are kind of best on average, rather than the absolute best peak. And so that's an important distinction. I think another important thing to remember is that a lot of these information theoretic approaches like AIC or BIC were all really designed for models that only had fixed effects parameters. And so they're fixed effects because you can, if you have an intercept and a slope in your model, you can count out on your fingers how many models you have or how many parameters are included in your model. But if you're including, say, a random effect in individual, for example, we don't necessarily know exactly how many parameters. The number of parameters isn't discrete anymore. So I think because of that distinction, it becomes not quite appropriate to apply traditional AIC to these models with mixed effects or state space models even. And so they're all kind of approximations that we should be aware of. But there's alternatives to generating those kinds of AIC-like things for those more complicated models. In a Bayesian world, though, we don't really have to worry about that situation. And so if we're fitting a model with fixed effects or fitting a model with random effects or mixed effects, we can use the same kind of information theoretic approach, but just do the whole thing in a Bayesian setting and make it easier. So this field, again, it's in some ways it's very old. Bayes factors were something that were proposed a long time ago, but even these other tools have been around for a while. I think when I was in grad school, DIC, or the deviance information criterion, was really popular, primarily because of its easy, it was easy to use. It was something that was available in WinBugs and JAGs. But over the last 20 years, I think we've seen a big change in these methods, and so it's a rapidly evolving field. 10 years ago, people were using WAIC, which was also available in JAGs or in STAN even. And then now in the last, say, 5 years, I think the field has kind of shifted again to using this leave one out information criterion, or LUIC. And so I think this is kind of considered to be the metric to use for best practices right now if you're doing a Bayesian model. But I'm sure if we were to teach this class in 5 years, the answer might be different. So, whoops, what just happened? Sorry about that. So there's a lot of, so there's lots of focus right now in ecology and fisheries on prediction and the importance of being able to create a model that generates good forecasts. This is just a list of papers that have come out in the last 5 years or so, a very small subset. I think that, as I was talking about last week with like the NEON forecasting challenge, that whole effort involves, there's lots of people involved in that effort. There's hundreds of people participating, and they have lots of different competitions. And so these kinds of competitive things have really arisen in other fields. First, there's a series of these M competitions in kind of the time series world where people are given a large number of candidate time series data sets, and they basically have this forecasting competition. And this is kind of the first one that we've seen in ecology, but it's not really a new idea. It's just something that's becoming more popular. So when we do that, when we try to design a model for doing that cross-validation, there are some resampling techniques that get commonly used. And so just the jargon behind each of these is kind of, a jackknife is not something that we're going to be doing, but it's something you can do in other statistical fields. Bootstrapping is something that we're doing in like MARSS models, and so it often involves resampling. And then there's cross-validation, which I'll talk about, where we divide our data set into some numbers of partitions, which we call folds, and then we ask kind of in turn, how each of our folds is predicted by the other remaining data sets. And then finally, we can do a data split in terms of if we're only interested in forecasting, for example, we can split our data set into, say, leaving out the last 5 years of data that we have, making predictions on that, and then using that to evaluate the model ability. So for bootstrapping, we know what we basically want to do is, in the context of time series models, we want to use bootstrapping to create pseudo data sets or new data sets. Last week I was talking about with a Bayesian model how you could do a posterior predictive check where you do MCMC to estimate the distributions of your parameters given your data, and then for each of those MCMC draws you can generate a simulated data set and then look at how well your how the attributes of that simulated data set across a large number of MCMC draws approximates the data that you actually have in hand. And so you can use that as a tool for model checking. But with bootstrapping, what you can do is, we could fit a model to Mars, and then do this bootstrapping where we can simulate new data sets, fit models to those data sets to generate new parameters, and repeat a large number of times. And so these kinds of bootstrapping procedures are really popular in state-space models where we want to use our estimated deviations from the model to or errors to simulate, and this is useful for estimating confidence intervals for things like our trend parameters or some of the parameters other than our states, the trends or the loadings or in a DFA, for example. And so the tools that we can use in Mars to do that are some of them are down below, but they're also available in other packages. So like the forecast package for time series data uses this as an option as well. So just to illustrate an example of this, there's a data set in R that's publicly available. It's called the Beavers data set. It's basically put some biologists put temperature loggers on 2 beavers over the span of a week, say, and then they have these are basically body temperature measurements taken at kind of irregular intervals. And so this is just using a subset of the data. This is just a temperature from one of those animals over a 12-hour period, and we want to use k-fold cross-validation to predict to kind of look at predicting temperature. And so just to kind of walk through how this is going to work, the first thing we need to do, kind of outside of the k-fold procedure, is to choose a model. And so in this case, I'm going to fit a simple state-space model using Mars. We're going to include an autoregressive coefficient, so the B parameter, and we're going to include the level or the trend parameter, the U. And then what we'll do is, with our k-fold cross-validation, once we have that model selected, we'll partition our data into folds. We'll do that randomly, and then we'll look at the ability of each of the kind of holdout data sets to predict each of the folds in turn. And so this is kind of the ugly way that I would do it in using a loop. And so in this case, we're just going to use the sample function here to sample our k folds. We're doing this with replacement, and so each fold is just going to each data point is going to get randomly assigned to one of the 5 folds. And then we're just going to kind of loop through each of those folds. The way to do this in Mars is, you can include data points as NAs, and so we're just going to loop through the list or loop through the k folds, and then when for each fold, we're just going to set the data to NA, make the predictions, and repeat. And so we'll just store the predictions and the standard errors. Okay, so this is what we kind of get out of this. The black lines here are the predictions, and the red lines here are the actual data. So we can see that, I'm sorry, I got that switched. The predicted is the red, the observed data is the gray. That makes sense because the red line is a little bit smoother in a lot of these places than the gray. And overall, we do a pretty good job of making those predictions. But then there's a question of, in that application, I picked k was 5. I did that totally arbitrarily. But in practice, how large should K be? And so there's this, again, this trade-off between the bias and the variance. And so when we have a low K, so if K is 5, we have low variance, so we can make really precise predictions, but we also are going to have larger bias. We're going to miss a lot of the variability in the data. Another kind of upside is that if we only have to fit this model 5 times, it's going to be much faster to run. And I think a K-fold of or partitions of 5 to 10 is kind of in line with what a lot of the machine learning literature says. So I think that's probably on the low end of what you would really want to ever do. In contrast, there's kind of the high K scenario, and the extreme version of that is leave one out cross-validation. But with a data set like this, it has, there's 87 data points. Maybe a high value of K might be 20 or 40, where we're holding out pairs of points, for example. And so when we do the kind of the high case scenario, obviously we're fitting the model a lot more, so it's computationally expensive. We generate models that are more complex, so they have low bias, but they also have high variance. And so there's no right answer here for doing this. I typically, I think that the leave one out cross validation is kind of what's commonly done in a lot of these applications. But in thinking about some of the kinds of questions I was talking through in the lab last week, where we had this enormous data set of temperature and oxygen measurements from that lake in Florida, and there's 900 observations. If you think about doing leave one out cross validation for a data set that large, it's really just going to become overwhelming to kind of loop through all the iterations and think about not just finding the overall best model for a set of lags, but what predictors or what other factors might be influencing temperature. All of a sudden, it's just become overwhelming. So there's no right answer, but here's kind of the results for comparing what this would look like if we did 5-fold cross-validation or 20-fold cross-validation. And so 20-fold cross-validation is in blue. The 5-fold is in red. As I said, I think that, we're going to get overall pretty similar predictions, but we're going to get more precise predictions when we, in general, we're going to get more precise predictions when we use the 5-fold approach. The trade-off there is that we're going to also get more biased estimates when we're using the low number of folds. And so the one place where we see the bias is kind of over here on the right, about that's about time step 2200, say, where we have the lines are diverging quite a bit. The blue lines are closer to our data points, which are up here in gray. The red line with 5 folds doesn't do as well of a job predicting those, or that change, for example. So that's one of the obvious places. But overall, whether you're using 5 folds or 20 folds here, you're getting basically the exact same model fit, which is probably not terribly surprising. These results will also change if you change. So this was just based on one realization where I took each of the data points and I assigned them to random folds, whether, in the 5-fold approach, each data point is assigned a number from 1 to 5. If I were to change the seed and repeat this, I would get a potentially totally different fit. And so you'd want to ideally repeat that a large number of times to kind of weed out that effect of just kind of the sampling error. Okay, so so as I was saying, ideally you would want to not just do this once, but do this a large number of times if you're doing 5-fold or 20-fold cross-validation. There's a lot of packages in R that will do this for you, and so the Caret package does this for a large number of models, including some basic time series ones, and there's a lot of other things out there for doing this sort of resampling. So in Caret, the way to do this is there's, it basically will let us set the number of, if we want to do this repeated kind of cross-validation, we can set the number of repeated iterations of this that we want to do. And so in this case, we're gonna just fit a model, for example, with 5 folds or 5 partitions, and then we'll just repeat that 20 times. Obviously, it gets very again, really overwhelming if we're doing this a large number of times, because just doing this once with 5 folds means we have to fit a MARSS model, for example, 5 times. All of a sudden, doing that that whole procedure 20 times means we're fitting the model 100 times. So I think these are useful tools, but it's also something to be aware of as you're going down the road of fitting very complex models. Okay, so what about for time series data? I think with the Beaver data set, one of the challenges is that the points that I was selecting or assigning to folds were totally random. And so I was just drawing numbers from 1 to 5. I wasn't taking into account the time series order or potential autocorrelation. And so that's an issue that is kind of unique to time series data, but it's something we need to account for. Okay, so the first kind of procedure that we could think about is kind of leave timeout cross-validation. And so leave timeout cross-validation would, if we're collecting, say, working with, say, our harbor seal data from the MARSS package, we have 5 time series monitored over a 30-year period. And we could think about, in turn, instead of assigning each data point to a unique fold, we could just, or a random fold, we could just take a whole year and drop them out in turn, and then fit the data to predict those holdouts, and just do that sequentially for every year of the data set. So this is a useful tool for analyzing or making predictions. It's important to emphasize that when you're doing it in this framework and basically holding out each year in turn, you're using both historical and future data to predict the missing observations. And so, I'm just going to again demonstrate this by reanalyzing the Beaver data using this kind of approach. So when we apply, so this is again leave timeout cross-validation applied to the Beaver data set. Because this is a univariate example with just one time series, we are basically going to be doing leave one out cross-validation. And so because we only have one data point for each time step, it's equivalent to leave one out cross-validation. If we had multiple time series, though, we would be potentially we could leave out the data points from the same time slice. So this is sort of what the differences are. So the red lines here, if I scroll back, are just, this is kind of what the predictions look like from the leave timeout cross-validation. So here we had 87 data points. I kind of looped through and fit the MARSS model to the data set 87 times with each time point held out. And then all of the predictions, the red line, is made from predicting each point based on the remaining 86 observations. So that's what this looks like. We fit the data, it looks like, perfectly, and we can look at how we kind of compare when we look at what's going on with the full data set. So this is actually, I think that my gray points here are wrong. I think I think that I needed to change this. I think the gray points here shouldn't fall exactly on the red line because the fit's not perfect. I think what it should look like is this plot where, again, we have, focusing on the red line is just the predictions from the leave timeout cross-validation. The gray points are the observed data. And then to contrast versus the MARSS fit to the full data set, I fit the model using the entire data set and then plotted these are 2 standard errors around the mean state for each kind of approach. And so I think the 2 things to highlight here are that when we're fitting the model with the leave timeout cross-validation, we're actually missing some of these points by quite a lot. That's not the case when we're fitting the model to the full data set. We're fitting the data perfectly, and we're getting very precise predictions around the estimated states. And the reason for that is that there's a lot of information also in kind of the time slices in terms of those means. And so when we're doing this with multiple time series, if we're holding out entire time chunks one at a time, or doing that in groups, there's a lot of information there about the mean of the state in that missing time period. And so I think here, we're just not doing a good job when we're obviously when there's extreme data points, basically. So that's not surprising, but so the leave timeout cross validation was kind of one approach. The second that we'll talk about is kind of leave future out cross validation. And so this is different from the leave timeout cross validation in that here we only are going to be evaluating model performance based on how well it can predict future data. And so in the leave timeout cross validation, we are holding out every year in turn, but using future data to predict what our missing observations would be in addition to using past data. So the way to do this would be to take, to take your data, divide it again into folds, say that each, if you have 50 years of data, each fold is going to consist of 10 years. We'll use the first 10 years then to predict years 11 through 20, then use years 1 through 20 as the second fold to predict the next 10 years of data, and so on and so forth, until finally we're using the first 40 points to predict the last 10. And so this is leave the future out cross validation is more appropriate for applications where we are just going to be focused on forecasting rather than both forecasting and prediction. Okay, so again, we can do the same kind of thing with the Beaver data set. Here, I'll just be partitioning the data set again into these 5 folds, but I'm doing this in order so that those 87 points are roughly assigned to into bins that are of equal length. So very different result from what we were getting with the leave timeout cross validation, in part because we're now trying to predict not just a single missing time slice. We're trying to use the first 10 years of data to make a prediction over the next 10, and of course that's going to be missing a lot of the kind of the randomness of this process. The other thing we see is that for each of these, as the pink line, the first pink blob, for example, represents the variance of our predictions for time steps 11 through 20, for example. And what we see here is that as we get, if we're using those first 10 data points, as we get further and further away from truth, the uncertainty is just going to balloon because we become more and more uncertain as we kind of as we increase in time. So that's something that we see for each of these folds. Doing this with 5 folds is obviously very coarse, and so if we were to do this in practice, we'd probably want to use a lot more. But I think this is essentially how one would do this for this kind of data. So using this in a Bayesian sense, as I said before, there's this kind of LU-IC, which is the leave one out cross validation, generally preferred over alternatives. But both this and WAIC are available in the LU package in R. And this is something that, there's a lot of vignettes and things out there that I don't need to get into today, but that's other things that you can read if you're interested. So, given that this LU package is out here, LU is super convenient. We can take any of the models that we are using for this class. So like the univariate models that we can fit with the ATSA package, or the Bayesian DFA models that I was showing last week, or the Bayesian MARSS models. Those are all stand fit objects that can be fed into LU very easily, and the LU-IC gets returned. And so, given that that's super convenient, it's also very fast. It takes a couple seconds to generate estimates of LU-IC. So given that that's the case, why would we ever need to use anything other than this LU-IC? So the leave one out information criterion is it's definitely an approximation to real leave one out cross validation. It's an approximation because if you were to do real leave one out cross validation for large data sets, especially in a Bayesian framework, it gets very, very slow. So it's ideal in that regard. But downside is that it can be very, very unstable for very flexible models. And so, unfortunately, a lot of the models that we're fitting in this class are these state-space models, or hierarchical models. And when we apply LU to the leave one out information criterion to those kinds of models, there's often warnings that get thrown, and you'll want to pay, especially if you're doing your class project or doing your dissertation in a Bayesian framework, you need to be really aware of these warnings when you see them. There's a diagnostic called the Pareto K diagnostic or statistic. And essentially what this is kind of a weight that the procedure gives to every observation in your data set. And the weight is generally between 0 and 1, but it basically will flag data points that are poorly approximated by your model. And so by poor approximation, the general assumption here is going to be that it's going to fit essentially a smooth Pareto distribution to each of these posteriors. And in cases where that's a bad, or where that is a mismatch, it's just going to throw you this warning, or assign them to kind of bad, basically label them as bad. And so I think instead of using, I guess, so something that's frustrating is that if you want to fit time series models or state space models, while Lua is out there and Lua's available, unfortunately, you often will need to basically write the code to yourself to do the real cross validation, which is much more time consuming, but it's also much more robust. So I found that that's, especially with fitting any of these Bayesian MARSS models, you have lots of parameters, lots of states to estimate, and so using this kind of cross validation, it's time consuming, but it's often the only way that you can do things. Okay, so part of that cross validation in a Bayesian sense is you'll see this expected log posterior density, and so this is not something we need to get into, but it's essentially the log probability of future held out data, given our posterior estimates of theta or parameters, and we're going to be integrating over the parameter space. And so that's essentially all the expected log posterior density is doing, but it's useful and it's widely applied in both the leave timeout cross validation and leave future out cross validation settings. When your posterior distribution is multivariate normal, this in a Bayesian world acts exactly the same as what AIC is doing, and so these things should converge and have very good performance for one step ahead forecasts. But when your posterior is not multivariate normal, then they're gonna diverge, and it will really show you the differences between AIC and kind of the Bayesian analogs. Okay, so finally, what we're going to do is talk about evaluating the forecasts or evaluating the predictions using these time series type frameworks. So if we were to do something like fit an ARIMA model to, this is just a time series of global temperature, and we wanted to make a prediction for 10 time steps ahead. This is the kind of plot that we could make with our forecast as the blue line. And we can calculate any number of kind of summary statistics quantifying how well we make that prediction. So, mean squared error is super popular, which is just the difference, or it's the expectation or mean of the data minus our predictions squared. There's variants of this like root mean squared error, which are very commonly used. And one of the nice things about the mean squared error or RMSE is that we can think about the linkages to AIC and tools like that for model selection. So mean squared error can be rewritten, and we can take this form here where we take the expectation of the the squared difference, but it also can be expressed as the variance plus the squared bias. So so in general, we want smaller MSE just the same way we want smaller AIC, and that will give you the model that minimizes both the bias and the variance. So, I think that in terms of quantifying forecast performance, another thing to think about is also that, any of these metrics can be calculated for single data points. And so if we were to, thinking about, for example, the neon challenge I was talking about last week, we were trying to make forecasts that were 7 days ahead, basically. And so one way to calculate performance would be to just focus on the prediction on the 7th day. So how well do you predict that single point? Another way to think about it would be maybe not just focusing on where you end up, but kind of what your path was to get there. So calculating mean squared error or RMSE on every data point over the forecast horizon, so over the 7 time steps. And you can do this, any number of ways like this. There's no right answer, but it is going to affect kind of the model that's selected as being as having the highest predictive ability of the ones that you look at. So there's all kinds of variants of root mean squared error. We don't need to talk about them all. There are different properties, and some of them are slightly better than others, but overall they're going to give you very similar performance. One of the other families of these, though, are what's called scale independent measures of performance. And so if we think about using MSE or root mean squared error to compare to compare the predictive ability of different models, and we have time series data that are very different in scale. In this case, if we had kind of unscaled abundance of 2 fish populations, the fish population that is indicated with the red line is going to give much more weight to that mean squared error calculation than the blue line, so it won't be equal. And so one way that people have, so it won't be equal. It'll be dominated by the red line. There's all kinds of other kinds of things that we think about outliers too, not just comparing one time series to another, but looking at outliers within individual time series. And so in this case, if we had something with a really high extreme, like in this case, this is chicken wing consumption over the course of a year with a spike at the Super Bowl. These kinds of outlier points are going to have a high effect on MSE or RMSE. So the other kind of family that people use to quantify the performance of these models is what are called percent error statistics. And so these are just looking at, instead of the squared difference, looking at the percent error. And again, there's other families of these, like mean absolute and root mean squared percent error. In each of these, we're taking our error, which is the difference between our observed and predicted values, multiplying by 100. And dividing by the observation. So the issues here are that there's several issues. One is that anytime your data are really 0, this is kind of undefined. So we can't calculate that. These things tend to be really skewed and have long tails. So generally, I think that these are not statistics that we want to use to calculate performance. I think that mean squared error, root mean squared error are usually better. But then there's also this other family of statistics. The third family is kind of these scaled error statistics. And so scaled error statistics are defined as the numerator here is essentially our the predictions, and the denominator are essentially the mean absolute error from a random walk model. And so we're basically comparing the predictive ability of any of our models to similar predictions from just a kind of a naive random walk. And so if we can do better than the random walk, those are obviously the models that we want to identify. So this is, in terms of interpreting these values, going back to this this equation, when these values are greater than 1, we're going to get worse performance than the random walk model, and when they're less than 1, we're going to get better performance. We want this value to be less than 1, where we're getting small errors on top compared to the large errors here for the random walk model on the bottom. So these kinds of approaches, the ACE and the MACE, are also available in a lot of the time series packages that we've been working with for this class. I think that, just as an example, we can go back to the air miles data set. If we do the auto ARIMA, we're going to be using AIC to kind of fit the model that, or find the model that that has the lowest AIC across the different AR and MA components. Here we're holding out the last 3 data points for that example. And this is kind of our forecast that we can generate with those 3 points with uncertainty. And then we can use the holdout data, or the 3 points that we held out, to evaluate the accuracy. So there's a cool function in the forecast package called accuracy. And what we can do with it is take our forecasted object, take our held out data, and then look at basically calculating our test statistic. And we can specify with the last argument whether we want the test statistic, like root mean squared error, calculated over all 3 data points that we're holding out, or just using the last data point in the series to calculate that metric. So here we have kind of the output from that object. And what's cool is that it gives you basically all of the different metrics that I talked about. So root mean squared error, mean absolute error, the mean absolute squared error, everything is being spit out. We can change this argument then to just, if we just cared about not kind of the path of the last 3 points, but what the value was for the last held out point, we could just specify test equals 1, and we would get get slightly different output. But that's essentially how easy it is to change the forecast horizon. So these things are very easy to get out of the forecast package for these ARIMA type models. If you want to do them in MARSS or something, you have to write the code yourself, but it's not that hard. And I think we actually already have some of that together for you. So the take home for these MSE versus MAPE versus MACE statistics, are generally that use mean squared error and root mean squared error when you can, but it shouldn't really be applied if you have data of widely different scale. And so again, if you have time series that are not standardized, for example, or one time series that has a lot of missing values, or things on different, basically different scales, that is a situation where those can be problematic. In general, these ACE and MACE statistics have been found to be a little bit more robust across simulated data sets. And so I think that's kind of, that's the best practice probably. But there are situations where you're also going to get very similar performance to mean squared error or root mean squared error when you do each. All right, so that's the kind of the MACE statistics, and the last kind of family are these things called scoring rules. And so if we think about what the mean squared error or RMSE is doing when we're evaluating predictions, what we're evaluating is the difference in our prediction versus our observed data. And we're only using a point estimate for the prediction. We're not using any uncertainty metrics associated with those predictions. So if we wanted to bring into account not just where we're predicting, but how uncertain we are, we could use these things called scoring rules to evaluate those predictions. So there's a couple papers here that I've linked to. There's a book by Draper and a paper by Knighting and Raftery that are really good overviews for how to use these things in practice. And there's, fortunately, there's a couple R packages that have actually implemented these. And as I'll show on the next slide, you could do this yourself too. It's not terribly difficult, but they're widely applicable for lots of different kinds of models and lots of different kinds of distributions. The other thing I'll say is that they're not limited to Bayesian models by any means. You can apply these to maximum likelihood methods. The one kind of dimension where they are limited is that these are going to be just applied to parametric methods. And so if we were doing something like random forests or neural networks or some other kind of machine learning tool where we weren't generating standard errors or predictions around our population states, for example, then we wouldn't be able to use these types of approaches because we wouldn't have any uncertainty measurements around our predictions. So we need something like MARSS, where we're getting not just our state estimates, but our standard errors of our state estimates out, or our, the posterior distribution of our estimates in a Bayesian world that we could calculate quantiles on. We need some measure of uncertainty. Okay, so this is sort of what this would look like in practice. So if we were making some prediction of, say, population state, for example, we would have some distribution represented by the black line here, which would represent essentially how likely that was. And so if this was the distribution of, say, the kind of an unseen population size using MARSS, we would make a prediction, we'd have some mean, which is kind of the mean of this distribution here. And then we would have standard errors around that. And in the kind of the MARSS framework, we assume that state is normally distributed. And so that's what this black line here is, just a normal distribution. And maybe the mean was 2.4, for example. So we estimate the population size was 2.4, and the red line here represents where we actually observe data. And so what we want to evaluate is how likely our data were given the prediction that we made with the black line. And so what that log score is going to represent essentially is the height of this distribution at that red line. And so it's going to, if we were to put a point here, it would be right where these two lines intersect. So that's great. Where I think it makes it probably a little bit easier to think about the differences here if we're starting to compare two different predictions. And so the two different kinds of predictions here might arise from two totally separate models, for example. And so the black line here maybe represents the prediction from a MARSS model with drift, and the blue line might represent predictions from a MARSS model without drift. And so again, we only observed one data point. We observed, or this is where we observed data. This black line, the height of it would be, our log score would be where these two lines intersect, and for the first model, and then for the second model, they'd be lower. And so because I guess I use these examples because the blue line here is actually closer, so it's closer to truth. It's actually centered on the value corresponding to the observation. So it's unbiased, but it's very imprecise, right? It has much wider tails than the blue distribution. So the standard errors from this model would be large. The black line, in contrast, is slightly biased, so it's kind of missing the mean, but it's much more precise. And so because of that, if we were to calculate the log density here versus the log density for the blue model, the log density would be higher for the black one. And so even though we're slightly more biased, it's taking into account the precision of that estimate. And so we would get this would be the black model would be favored over the blue one in this case, because we're balancing both the bias and the variance. So we want predictions that are not just unbiased but also precise. All right, so we can do that again, like I said, in a frequentist or Bayesian setting. And I think for the for the kinds of competitions that are being done with, like, the Neon Forecasting Challenge, for example, they're relying on these same kinds of metrics to do predictions. So they care about not just how accurate your predictions are, but whether or not you can actually create forecasts that are also precise. So that's kind of a cool thing, and I think that they're using the scoring rules R package to evaluate the predictive ability of different models. All right, I think. Yeah, so I think that's all we have. I'm gonna stop sharing my screen.